Last week, I had a meeting with a former colleague of mine from my TV news days back at KDKA, and we were talking about what's going on in Pittsburgh in the future, and she said, you know, I just turned 40. My husband and I just turned 40. And she said, we were out to dinner, and my husband turned to me and said, we are so old. So there's all these 28-year-olds that are doing incredible things in Pittsburgh right now, and we don't even know everything that's going on around town. And first off, I assured her life does not end at 40. She still has a very bright future. But what they said is very true. It's amazing to see what's kind of happening here in our own innovation ecosystem here in Pittsburgh today. Well, we're going to go shift again just a little bit and continue our conversation about, in this case, energy, water, and the petrochemical revolution that's really happening worldwide, but especially here in our region. It was only, I guess, 2004, so what is that, 13 years ago, a little over a dozen years ago, that natural gas was discovered in the Marcellus Shale, and it suddenly vaulted Pittsburgh back into its historic position as a leader of the global energy revolution that goes all the way back to the 1850s when the world's first oil well was drilled here. So the purpose of our next panel is really to talk about what's happening now, what's ahead, and what it means not just here in our region and in the United States, but also obviously what it can mean around the world and especially in the Middle East. And we have a terrific panel lined up to take on this part of the conversation. I'm going to introduce them one by one and invite the panel to come on up to the stage here. They'll come up as I introduce them. Yeah, first off is Dr. Johanna Schmidtke, who's investment director with Saudi Aramco Energy Ventures. Come on up, please, find a seat. Next, Dr. Brian Anderson, Director of the Energy Institute at West Virginia University. And Dr. Jay Whitacre, Director of the Wilton Scott Institute for Energy Innovation and a Trustee Professor in Energy and Materials Science and Engineering and Public Policy at Carnegie Mellon. And Dr. Michael Ziemkiewicz, the Director of the Water Research Institute at West Virginia University. And then finally, Mr. Michael Lordi, the Chief Operating Officer of Elliot Group in Jeannette. That, for those of you from out of town, is about 30 miles or so east of Pittsburgh. And welcome. Good to have you all here. Let's talk a little bit about the revolution that's been ongoing now for quite a period of time. But, for our region anyway, Dr. Anderson, it probably did start in 2004 when somebody struck gas, and all of a sudden we realized there's a whole new world out here in terms of petrochemical opportunity. But what were the technology, the innovations and initiatives that sort of unlocked that possibility, and how is it shaping what's unfolding right now in the world of petrochemicals?
Well, what really kicked it off was the combination of horizontal drilling as well as hydraulic stimulation. And so with long laterals and horizontals, you were able to access a lot of surface area of rock, and then with fracturing, you could open up a rock that really didn't flow a whole lot until you fractured it. And so those technologies have continued to advance over the last 10 years, 13 years, to really make it much more efficient, where companies are drilling extremely long laterals now and optimizing the process. And we had a project at WVU that kicked off 2 years ago with a number of industry partners to try to continue to optimize that process. And so what it's kicked off not only is the natural gas that we're producing, we've now created what, if you add the Marcellus and Utica, it rivals the North Field shared by Qatar and Iran. And so what is kicked off is the liquids that are flowing out are now the lowest cost feedstock for the petrochemical industry on the planet. The ethane that's in this region comes to about 4 to 5 cents a gallon for ethane. In Texas is about 21 cents a gallon. And that's simply because of the oversupply of these natural gas liquids. And so this really is an impetus for a huge build out of the petrochemical industry that could come in the very near future. And if I might mention, the American Chemistry Council released a report earlier this year that based on the Marcellus and Utica, there is a potential of $36 billion of investment in the petrochemical sector, adding 101,000 jobs across the region just based on this resource and the potential in the petrochemical sector.
So does a market exist for all of that, and how well equipped are we to get it to those buyers if they're out there?
Well, one thing that's really surprising to most people is that 70% of the demand of the petrochemical product, the polyethylene, in the United States is actually here in the Northeast. And so our current model is we convert ethane into ethylene and polyethylene, mostly in the Gulf Coast, and then ship it up here to the Northeast, where if we build out a second major petrochemical hub here in our region, what that does is it puts the Gulf Coast at a price point where there's a lot of potential for export into markets in Europe and South America, and even parts of Asia. And so it's really supplying the domestic from this region and then the export market from the Gulf.
Interesting. So really some potential synergies actually between those two great industry centers as that develops, yeah.
Absolutely. And there's a lot of support for building out the industry here in addition to in the Gulf.
Yeah. Dr. Schmidtke, I wonder from the perspective of sort of the global situation and all of this, how do you really see this playing out and affecting what's happening around the world when it comes to petrochemical?
Well, certainly there's a revolution underway. Working with the investment arm for Aramco, we have looked at petrochemical opportunities in the earliest stages of the fund as it was set up 5 years ago. As Aramco looks not only to diversify into the bulk production, but also looks at marketing those. And so, how do we invest, help them as an investment arm to invest in technologies that will enable blending components or additive components that can raise that level of the product. So, for instance, we've invested in a company here in the Northeast based out of Boston called Novomer, where you're making an advantaged polyol out of CO2, and that polyol is able to, in foam instances, be able to elevate the value of the foam coming out of the bulk facilities and the polyol facilities that are being built out within Aramco. So you look at different technologies within the petrochemical space, and I think not only do you have plays here in the U.S., but as others look to diversify out of simply bulk materials or out of core products, looking for additions and add-ons in the technology space that can elevate the value of what they have into a broader suite of chemicals available from the company.
And you find those opportunities or those technologies out there right now, and what kinds of other specific examples of where some of those opportunities are?
Well, that one's quite nice. It was one of our first investments, and Aramco actually acquired half of the company at the end of last year. So that was, I think, a unique early hit for us. But we have invested in other technologies, for instance, in the refining space, where if you have heavier crudes, you need to be able to elevate the products that you have, and so being able to take heavier crudes and process them through a facility at higher efficiency. And we've invested in the catalyst space, again, another company out of Boston. But we look for those type of add-ons where you can take a very large facility that's running on large volume products that come out of a company like Aramco and drop in specific additives that really elevate those existing facilities rather than having to build wholly new ones. And so while certainly wholly new facilities are being constructed every single day within Aramco, there's also that opportunity to elevate the facilities that already pre-exist.
It's interesting. I know we've been blown away here in the region, having now been here for 35 years, at the sheer scale of the Shell Chemicals investment that's happening about 30 miles down the road. You're talking billions and billions of dollars. We really haven't seen anything like that in our region, maybe since the Second World War. And it just speaks to, you got to be careful about those big capital investments. If you can find other technologies to help avoid that, that would seem to be really important these days.
Yeah, that's certainly been part of our thesis, and we've also invested in some of those bigger plays, and we'll see where they go.
One thing I've learned from hanging out with folks at Pitt and CMU and WVU and just experts in the space is you can't talk about energy without talking about water. And I wonder, Dr. Ziemkiewicz, how water really relates to both conventional and unconventional, and how it's going to play in this whole evolution of technology going forward.
Well, if you think about the typical conventional gas play, you're not injecting any water in the first place. And during the production cycle, you always bring some water back with the gas. And that creates an entirely different dynamic. The volumes of water are relatively low. The water starts out saline, stays saline, whereas in unconventional, you're stimulating the whole formation with your injected water. And typically, you'll inject 5 to 10 million gallons of water. That's 20 to 40,000 cubic meters of water. And a lot of that comes back, not all of it by any means, but it creates an entirely different water balance. So you're getting not only the production water out of the formation, but you're always getting, I guess, some proportion of the water that you put in the first place. And that's another good example of how steep the learning curve has been in the Marcellus, for example. When I started talking to the industry back in 2008, 2009, and this is based on a small DOE project that we had, they were assuming that something like 30% of the water that was injected would ever return to the surface. And in fact, studies that we're doing now on another DOE-funded project near Morgantown indicate that it's only between 5 and 10% of the water that comes back. Now, that's very different than we have a project with Kansas University in the Southern Plains, also looking at unconventional oil and gas, and they're saying that in some cases they're getting 120% of the water back. So they're actually pulling a lot of water out of the formation plus some proportion of the injected water. So the water balances are really different from one part of the country to another. So ours is very saline. Now, when we talked to the industry also, they said, well, we really can't use that water for refracking or for subsequent frac jobs. We have to dispose of it in deep wells. So that was the thinking back in 2008. Chloride levels were high enough that they thought that would interfere with the cross-linkers and other components of the completion fluids. And it turns out that the industry adapted to that very quickly, so they were able to use more and more saline water. And as a consequence, something like 85% of all the produced water in the Marcellus Formation is repurposed for subsequent frac jobs.
So that technology's moved a long way in a relatively short period of time.
Incredibly fast, yes.
But I would think that would become very important in areas that don't have a whole lot of water, the more efficient you can be in using it.
Absolutely. And one of the things that the industry has been able to do is improve that efficiency, improve that recycle rate. For example, even chemically, the industry has found that the more saline the water, the actual better you get in terms of gas production, because if you put fresh water in contact with saline clay formations, the clays swell up and immediately close up, or some proportion of the fractures that you spend a lot of money making in the first place. On the other hand, if you use saline water, those fractures stay open much better. The other thing is that it's a denser fluid, so it helps pressure control in the formation. So these are really revolutionary notions that just weren't around 10 years ago. So again, you're right, extremely rapid progression of technology in this formation.
Yeah, well, it's been on the drilling side too. I mean, I was on a rig 6 or 7 years ago, and then the operator told me I could hit a softball 1 mile down and a mile out with this rig. And I understand the sophistication in the drilling and how far they can go has just changed dramatically in the last several years. Yeah.
Well, it certainly has. Now you can hit that softball 2 miles out and 2 miles down, or even 3 miles down. But the other big component of that is the speed at which we're able to drill now. And there's even a lag in technology at this moment where you can drill faster than the technologies that you're using to measure the formation. And so what you're continuously doing is measuring a bunch of different components of the rock as you're drilling to make sure you stay in the right target. And that was another major advance in technology. And to be able to do that in real time is a huge data science issue. Our project that Paul alluded to in Morgantown, we are actually producing 1 terabyte of data a day just in sensing from that well, and to try to even get your hands around not just the measurement but the analysis of those data is unfathomable.
And Dutch, do you see the same level of just technological advancement happening in the Middle East as well, in other parts of the world?
Sure. And as far as the drilling systems, because the wells in much of the Middle East are so large, a lot of the technology where, if you're in the Permian Basin, you probably don't put that much on in terms of the tool set that you put down. In Aramco, they'll typically run a lot of jewelry downhole because it's worth it on every single well as opposed to, mechanizing, drilling multiple wells. But you're absolutely right. When you look at the amount of data, 1 terabyte a day, and then you look at what the data rate is coming up a hole on a typical mud pulse system on 1.5 to 2 bits per second. you can barely, and plus the travel time from the bottom of the hole, telemetry is a massive issue. It's an absolutely gaping hole compared to what you're able to measure downhole, what you're able to put downhole and store downhole versus get up real time. It's one of the major issues on the technology side for drilling that we certainly look for solutions for that every day.
Well, I wondered about that. Is an area looking for investment as well, if you can find that big data company or whatever that figures that one out.
Call us.
You're in, right? Dr. Whitacre, we got so much gas, so much liquids. Where does it leave renewables in this world of plenty that we have right now?
Well,
We'll trade there.
specific to the Middle East, I think, is what's been fascinating the past 2 or 3 years is an explosion of interest in renewable energy as well, specifically solar. You'll see, depending on the location and the, report that you might read, there's, hundreds, tens or hundreds of gigawatts of solar being planned for places like Abu Dhabi and Jordan and Qatar and Saudi Arabia. And they are, I think, eager to diversify their energy balance just because there's a sense that they don't want to they've put all their eggs in one basket for a very long time. And I think, and they have a lot of money now to invest in other things. They are diversifying, I think, their energy portfolio. It's not clear what the best path for them renewable-wise is in terms of what they might do with the solar energy, because they already are producing a lot of electricity with fossil sources already. But I think shedding some of that and moving over to renewables is an obvious choice.
Well, it does at some point, it turns their fossil fuels into an export opportunity. They've got the sunshine there to grow their economies. Right?
It offsets, right? It could also power a fair amount of their processing that they're doing on site as well. So there's many reasons to do it. And the last thing is converting things like other resources like water or other things that are very useful, but maybe not direct energy use.
Makes sense. Mike Lordi, you're actually in the business of making equipment to support this global industry. What's been happening in your world as all of this has evolved in recent years?
Well, in our world, of course, we're interested in what you do with it after you get out, after it comes out of the ground. I think the International Energy Agency predicts that even with all this extra production, there's going to be a shortage of oil by 2021 at the current rate. So there needs to be more processing capability as well as more pumping and drilling capability. For us, we see the location of this oil supply in the U.S. really supporting not only the Shell ethane cracker, but I think 1 to 3 more. I think some of my colleagues up here would say more than that, but at least 1 to 3 more plants in the next 5, 6, 10 years. So it's a fascinating process, and I think there's nowhere to go but up.
There's been talk too, Dr. Anderson, about a storage hub of some sort here in somewhere in the region, the tri-state region?
That's right. Over the last year, we've been a team of geologists in the Pennsylvania Geologic Survey, Ohio Geologic Survey, and West Virginia Geologic Surveys worked together on a project to identify what some potential storage locations of natural gas liquids would be in the subsurface and the geology, and then what the optimal surface infrastructure would look like of pipelines that connect the potential sites of building crackers. Because if you run the numbers right now, the amount of ethane we're producing in the region, we actually reject about 350,000 barrels a day of ethane. By rejection, what I mean is you're putting it into natural gas pipelines where it's burned in your furnaces at home, it's burned in power plants. And when you combust ethane, it's a higher CO2 footprint than it is methane, just marginally. But the 350,000 barrels that we're burning today in power plants equates to about 3 million metric tons of CO2 a year that could be abated just simply by burning methane instead of ethane. And I'm a chemical engineer by trade, and folks in the chemical engineering space would say, well, it's a crime to burn ethane anyway because it's a valuable feedstock. And so the storage hub that we've been working on is to try to make sure that we have the infrastructure in place to support a robust industry in the region.
Does that look real? Does it appear that there's a pathway to build some of that?
It certainly does. Geologically, we have a few different options across the tri-state region, some in Pennsylvania, some in Ohio, and some in West Virginia, to be able to store the necessary natural gas liquids in the subsurface. And then, because of the great potential in the petrochemical space, there certainly seems an appetite to build it based on capital, based on the emphasis of the Department of Energy, as well as the 3 states. So the 3 governors of West Virginia, Pennsylvania, Ohio, all signed an agreement 2 years ago on October 13th of 2015 to work together specifically in this area to maximize the use and potential of our resource in the region.
I'm hearing about, all this, the engineering, the geology, the computational ability, and aspects with the big data and all those implications. I just wonder where, especially those of you from academia, where are we in preparing the people we need to do this kind of work and to fully develop the resource? I was struck by what Dr. Moore said in an earlier session about finding the people to do the work. In his case, artificial intelligence. In this case, this sort of petrochemical activity. I know in terms of Carnegie Mellon, Dr. Whitacre, you have a campus in Doha, in the Middle East. It seems to be more focused on computational stuff than this energy stuff. Do you see curriculum changing or evolving in some way?
Maybe. So there is, Doha's an interesting place in that there are many other universities there as well. There's several others that have emphasis on medicine or traditional engineering or computational science. So I think they've got the bases covered for that one spot. But as we saw recently, there can be issues, turmoil or otherwise, where maybe having a diversified curriculum elsewhere in the region could be useful too. And I couldn't agree more that there's, in general, I think a dearth of information and knowledge on how to execute on these energy engineering topics. We have also a campus in Africa and in Rwanda, and we also offer a couple of engineering degrees there, and neither of those are energy related either, and there's a huge interest there too. And so we're trying to figure out, can we triangulate and make an Africa-centric or an area, a regional play to educate folks on the key sort of practical energy engineering things that matter, and maybe some sort of like boot camp style training curriculum as opposed to a straight up academic curriculum, because we need folks who are out in the field executing on things, understand the theory and the practice of fracking, understand the theory and practice of renewable installation and maintenance, photovoltaics, hydropower, wind power. None of these things are particularly need a very deep academic preparation, but a more professional preparation that can and should be offered might evolve at some point. We are in a couple different sort of levels of talk around that.
Yeah, Dr. Anderson, I guess in WV, you've got a civil engineering program in Bahrain. I guess you also manage the U.S. Department of Energy's U.S.-China Clean Energy Research Center for Coal, numerous other agreements and partnerships around the world. How important are these partnerships going to be, do you think, especially in the energy arena?
Well, the energy arena is truly global. I mean, it's you look at the oil market, it's absolutely a global market. We look at the Paris Climate Agreement, really just shows a spotlight on the changing landscape of energy around the world, and many of the Middle Eastern countries are signed on to that, and leading to potential and current deployment of renewables in the Middle East. And so one thing that's really important is we educate students here in the United States, in West Virginia, and in the Pittsburgh region, is that they certainly have an understanding of the global markets, but also with the U.S.-China Clean Energy Research Center Advanced Coal Technology Consortium that we are running, we're now in the 7th year of that, it's a 10-year, $100 million project between the U.S. and China, is that we're working hand in hand, the world's 2 largest emitters of CO2, 2 largest users of coal, working hand in hand in developing new technologies to lower its carbon footprint. That's the mission of this particular program. And so it's really become a great partnership where we have companies, we have 10 industry companies in the United States, as well as companies, researchers, and SOEs in China, state-owned enterprises in China, all working together toward really a shared goal in developing new technologies. And so major problems require us to stack hands across the globe in order to tackle these major issues that we have in front of us.
Well, let's assume that you all are successful in churning out the next generation of folks we need to tackle these kinds of problems, both here in our region and around the world. What's the big challenge, the big innovation, the big opportunity that you see that you wish you had more brain power and more muscle and resources to tackle? And Dr. Schmidtke, I'll start with you.
Sure. Well, I'll I'll quote someone that I thought put it quite nicely. So I met one of the data scientists, relatively young at EOG, and he had been 5 years at EOG, and he said, yeah, all my friends are figuring out what color to make the t-shirt on eBay to make you more likely to buy it, right? That's the data scientists, that's where his colleagues had gone, and he's really looking at solving complex questions, and the same for the folks like EQT here in the region. There's an immense amount of data that's already been referenced in terms of not only what you can drill, but in the production that's coming up and the availability of on-site analysis, lab on a chip that's available at the well site, whereas before you would have had to send it back for a long time. That's just a very nascent space in oil and gas, whereas it's fully developed and highly developed in the healthcare space. There's a wealth of information that's out there, but you do start to get to a series of a very large data problem very quickly, where you also need to have a physical basis for what you're doing. And I think that's where the challenge becomes very difficult, because you have to have that physical model and a physical understanding of how things are being drilled, how they're being produced, what the effect of the long-term exposure to the chemicals are downhole, but you also have to have the data capability long-term. So to me, that is a fascinating question for someone who comes in from a data scientist standpoint. It's not one to be solved by one or even 100 folks, but it's a lot more interesting, in the end than the color of a t-shirt on eBay. But I do think that's a reality that you're facing, certainly with the market in Silicon Valley at the moment.
Let's talk about water. Dr. Ziemkiewicz, what do you think from the standpoint of the big opportunity, the big challenge that's on your mind that you wish you had more brain power to help with?
Well, the big challenge in water in this context is working against the laws of thermodynamics, which is to get salt out of water in a really efficient way. Right now, there are companies that are doing it, and I had lunch with two gentlemen from Aquatech in the room here. There are companies that are using more or less conventional technologies and making improvements on those, but there really needs to be a step change in terms of cost and in terms of performance. And performance is measured as throughput rates and the reject rate. Right now, a lot of technologies reject half the water that goes in, so all you're doing is concentrating some brines even further. And very many of those, it was mentioned that natural gas is used for water treatment in the Middle East. A lot of those thermal technologies for desalinization basically just boil the water off with varying degrees of efficiency, collect the condensate, and then turn that into, clean water. That still leaves you with an enormous energy burden. So how you can get from where we are now to the point where we can significantly drop those costs and improve the reject rate is, to me, really important. And it's important because I already mentioned that we are recycling a lot of the produced water that comes out of this formation. In other formations, like in Southern Plains, that's not the case. So there's always a need to find some way to get rid of that saline water. And even here, where the recycle rates are very high, if you're in a region, say 100-mile diameter region around your well, you can't afford to truck water that far. So you have to find some way of dealing with it near the wellhead itself. Otherwise, transportation gets you. And so there's that. And another technology that I think is going to be more and more important is reservoir pressure management, where this is something else we're studying with our colleagues at Kansas. We're looking at pulling water out of sort of less saline formations at depth, maybe much too saline for use in agriculture, but much easier to treat than produced water. Produced water is really bad to treat because it has a real rich chemicals too in it. If you can replace that water, maintain the pressure in the reservoir, and pull out easier to treat water that can run through a conventional technology relatively cheaply with a minor reject rate, then you can use that for irrigation, for example. So that's of great interest to people in arid countries. And that way, you're not collapsing your reservoir, you're not reducing its porosity, you're not causing land subsidence, you're not doing a lot of things that are otherwise bad. Another thing you can do with a lot of that produced water is use it for oil and gas reservoir pressure management too. So, and a lot of it is used that way, just to pressure up the reservoirs. As you're pulling oil or gas out, the reservoir pressure drops, and you have to do something to stimulate it and get that out. Otherwise, you can put in a lot of these produced waters and replace that and pressure that up so that naturally pushes the gas and the oil towards your well. So those are the kind of management and technology areas I think we have to go in to really get a grip on how to deal with this excess water.
Interesting. Excess water, salt in the water. Desalination, is that something that's top of mind to Carnegie Mellon as well?
Yeah, I think so. And just to add to this, there's an interesting overlap between available energy and methodology for desalination. Some of the wealthier countries that have more resources, both fossil and solar resources, can afford to do simple thermal evaporation condensation, true desalination from the water for drinking water, and they will then pump it places and use it for agriculture and so forth. A place like Israel, though, has far fewer resources, and they're extremely focused on innovating, doing next generation water technologies. We have a couple of researchers at Carnegie Mellon who have won some joint U.S.-Israeli grants to do just that, understand best-in-class membrane and defoulant and electrode structures for highly efficient desalination. And it's much more important for that country than it is for some of these other regions, just because they're so constrained both in space and in energy, and efficiency is everything. And so understanding the context of where you're doing the desalination, how you're doing the processing really matters. And it's interesting, and how you use you might use water for one thing and then you could just throw it away, or you might use it and then cleanse it to some extent and use it for something else. And understanding the technical price and energy trade-offs between those different options really matter. And we're also studying that at CMU.
Fascinating stuff. So Mike, Lordi, Elliot, you're out there trying to make a buck in this industry. What do you wish there was some more brain power? What keeps you up that you think, man, I wish more smart people were looking at this issue that I see that affects my industry?
Well, for us, we're equipment guys, and equipment is highly specified, engineered, lasts a very long time, and has very complicated control systems. The equipment lasts a long time. Control systems go out of date every 5 years. So in these plants where the life cycle of the facility is 40, 50, 60 years, now we have all these disparate control systems operating these processes, and for us, tuning the process, making the plants more efficient is critical, and you can only do that with controls. And controls require software, they require sophisticated algorithms to run the facilities and to link them together, because Shell ethane cracker is I call that an upstream plant, and downstream from that you have PDH plants, you have polypropylene plants, and those all have to interact together, and the better you can tune them, and the only way you can tune them is by information and getting the information uplinked to people that can see the whole process and not just this one plant. And to me, that's critical as we go in the future, because as we saw with the hurricane in Houston, a small disruption in supply chain has big impacts, not only in gasoline prices that consumers pay, but just general supply of materials in a pipeline. So to me, controls is the next big step.
Well, you're talking about going from knobs and switches to now these digital and screens and everything else. It's that whole Internet of Things idea, I guess, that all these machines are going to talk to each other. Are there safety issues that in your industry in particular you think you need to be thinking about as this evolves?
I think there's huge safety issues. These plants are very complicated. They require very close control. And as we've seen with in some other internet applications like with Equifax and even Yahoo, there's bad actors out there that could do harm if they could hack into a system, take control of a plant unbeknownst to the operators. I think there's some serious security issues that have to be addressed before we can really make the industrial Internet of Things work correctly.
Are you seeing this, Dr. Schmidtke, that's an evolving area as well?
Certainly, yeah. We spend quite a lot of time looking at the Internet of Things, Digital 2.0, the various names for it. And certainly the security issue is the cybersecurity issue for operational technology. So not just the IT side, but the OT side. Once you get beyond the air gap, you get into the actual systems of the SCADAs and the PLCs. How do you ensure the integrity of that? Now, if it's one thing if your PLC is measuring the temperature and spitting that back out to you. It's a whole nother thing if you start to write, very compact programs that are able to fit onto the memory of a PLC or a SCADA system or a security system, and now actually operate that plant and operate with control. Well, now you have to have a level of security at that operational level, and it's an area that continues to expand. I think in the U.S. you see it mostly in utilities in the general audience, but certainly for oil and gas, for all the majors, and certainly the large independents, it is an absolutely paramount issue that really has not yet to be fully solved.
Yeah, Dr. Anderson, I saw you nodding your head about that. You're seeing that as well? And
Well, certainly, cybersecurity through the industrial Internet of Things, as we become more and more connected, and we put more and more sensors into plants. And one of the big target, there's a U.S. Department of Energy program called, it was a Smart Manufacturing Leadership Coalition-led program specifically in advanced optimization. I know CMU's a part of it, and WVU, and University of Pittsburgh, and others. And the goal of this is to make a plant smart and adaptable, layer on artificial intelligence to where the plant can chart its own course. And so any little bug that could be placed into that could have major ramifications. And we certainly see it in the grid sector, the concerns as we become a smarter grid, one that is more efficient and is operating much closer to its limits to be more efficient. When we have a perturbation like the polar vortex a few years ago, we were just right at the razor's edge of losing a major part of the grid in the United States, and we did see a major blackout that started in Cleveland and made its way to Boston. And so all of these things are very interconnected, both through cybersecurity, advanced control systems, artificial intelligence, and I see that as one of the major challenges, and one in which I do want to see a lot of brain power devoted to it, for sure.
well, I'm thinking about Dr. Moore's presentation about AI and safety and how it's not quite knocked yet. I mean, these are very real issues as we deploy all of this. Anybody else? Yeah, Dr. Whitacre, you want to add to
I mean, just to lump on that, I think one of the things we often think when we think security, we believe there's some malevolent force out there after us. But the reality is, just when you put this many things in play in one space, interacting with each other, you can't always. There could be unintended consequences of a good design that rattle through a system and could cause chaos, depending on the degree of intersection between all these different interconnected things. And just being aware that there's, the devil's in the details, and the enemy might just be, an incomplete design as opposed to, a single person or a group trying to do bad.
Fascinating. Puts another twist on it. Big capital investment, complex systems, all kinds of ingenuity and knowledge to keep it running under all conditions so safety does not become an issue. You live with that every day, Mike.
Sure, and the other thing that maybe didn't come out so well is these plants have to run 24/7, and typically it's used to be 2 to 3 years between outages, and now they're looking 7-9 years between outages. And in fact, LNG plants, and like in Qatar, they're running 10-11 years between outages. So it's a highly complex dance that happens in each of these big facilities.
Pretty amazing. A minute or two left, if anybody has another question or comment or whatnot. Otherwise, I'm going to get us back on time. And thank our panel very much. Really appreciate it. Great conversation.